No? Okay, then we leave the questions for later, and Hong, please.
Yeah, okay, yeah, thank you. Thank you for the introduction. My name is Hoang Nguyen from Northumbria University. So today, as Lucas mentioned, I would like to show you the implementation in MoFEM, like just a brief about that, and the example that suits for the illustration would be the symbol Poisson problem. So here's the outline of my presentation. So first I will set out some goals of the presentation, then the theory of the Poisson problem. Then I will focus on the explanation of the different components of the implementation of the problem in MoFEM before showing you how to run the analysis and conclude with some summary. More detail of the theory and the implementation that I'm going to present here is provided in the tutorial SCL1 that you can find in the MoFEM webpage. So the goal of the presentation, as mentioned, I would like to show you the implementation of a simple Poisson problem in MoFEM, the code structures, two important concepts in MoFEM. They are pipelines and user data operators, of course, with the detail of the implementation. So I believe all of you here are familiar with Poisson equations. So it is used to model different physical phenomena, for example, steady state diffusion, heat flow, or electrostatics. So the strong form of the problem, you can see we have the divergence of the gradient over here of the field U that equal to the body force F on the domain omega over here, and here for the simplicity we consider the homogeneous boundary condition on the boundary d omega over here. So by multiplying both sides of the equation in the domain by a test function and then integrating by part, we arrive at the weak form you can see over here, where the test function delta u in the space H1 0. Then we have the field U is approximated by the linear combination of the safe function phi over here and the degree of freedom U bar. Then the global system is obtained, and you can see Ku equal to F, where K is the stiffness matrix, U is the vector of unknowns, degree of freedom, and F is the force vector. So I'm sure all of this one is very familiar for all of you. So these components of the element stiffness matrix and the force vector can be calculated using numerical integration, where you can see over here W is the integration weight and J is the Jacobian of the Jacobian of the transformation of the element between the parent and the global coordinates. We also have like a tutorial that you can refer to if you're interested about the numerical integration that you can find in the link here to the MoFEM webpage. So once we have all the equation derived, and we're now focusing on the implementation of the problem in MoFEM. So the primary function here, you can see the Grun program function that will include some other function that execute a series of tasks. So we have read mesh, and that will read the mesh, set up the problem, boundary condition over here, responsible for setting up boundary condition and applying boundary condition as well. Assemble a system function. It's responsible for assembling the system equation. We set then the function for the set integration rules. Then the function for solving the system of the equations, and then the processing is done in this function of output results. So now I will be focusing on the first function, the readMap function over here. So the first one that this function do is to get the simple interface that provide the functionality for the fast and straightforward implementation in MoFEM. There are other interfaces for more complex problem, but for simplicity of the current problem and the limit of time, I will focus on just the simple interface only. The function over here, get options, and the load files that are responsible to get the file names and load the file to the program. And over here, if, you can notice that we have the error handling. It is suggested by the keywords over here, MoFEM function begin and MoFEM function return 0 at the bottom. So this error handling in each of the equation in each of the function in MoFEM that would help user or developer quickly identify where the error come from if there is one during the compilation or the running of the analysis. The second function is the function for setting up the problem. So in this function, first we add the domain field, and in this domain field we have the name of the field, so we name it domain field over here. We have this space of the approximation, we use h1 for the scalar space. And here we have the base function. So in this case, we use the Bernstein-Bezier base as Lucas introduced. For the coefficient 1 over here, it's representing the number of coefficient per shape function. And here we have the scalar problem, so it is 1. It should be noted that here we just add the field to the domain only without the field for the boundary, as we use a homogeneous boundary condition for this problem, so no need to add the field to the boundary. But of course, if you use non-homogeneous boundary condition, then we need to add the field to that. Next one, regarding the field order approximation. So in the code over here, you can see default will be third order, but of course, user later, they have the option to indicate arbitrary order that they use by the command line options dash order over here. And finally, we do some like function to set up the problem. The next function is about the boundary condition. So two main things happen in this function. The first one is to add the entities where the boundary condition is applied, and then second one is to apply the homogeneous boundary condition to the block set of the entities. So in the first part, so we take all the edges that name boundary condition, for example, for this mesh. So we name that in the name the block set in the mesh, and then the code would take all the entities that associate with that block set, and then we add to that block set all the vertices that are adjacent to the edges that we get previously. Here you can see MoFEM wrap the functionality developed in MOAB library, and MOAB is the part of the Sigma library that developed by researcher at Argonne National Laboratory. For the second part of this function, we can see here we apply the homogeneous boundary conditions by removing all of the degree of freedoms that are associated with the block set defined above. For the assembly, this function is responsible for assembling the system. So here we introduce two important concepts in MoFEM. The first one is the user data operators, and the second one is the pipelines. So user data operators are where we implement functionality needed to calculate the left-hand side matrix and right-hand side vector. And the pipelines is where we push the develop user data operator to, and it will be used and executed throughout the program. So in particular, for this Poisson problem, we have two pipelines. So the first pipeline, you can see left-hand side pipeline over here is responsible for the calculation of the left-hand side, and the second one here responsible for the calculation of the right-hand side. And these two pipelines are managed by the pipeline manager over here. You can see in the code. Regarding the user data operators, we have operators to calculate the inverse Jacobian and the left-hand side matrix. These are two operators that will be pushed to the left-hand side pipelines. And the other operators here that are responsible to calculate the right-hand side vector will be pushed to the right-hand side pipelines as expected. Now we focus a little bit more on the detail what is doing here in the code in the user data operator and the pipelines. So for the operator that calculate the inverse Jacobian, and so the first one is responsible to calculate the inverse Jacobian. You can see over here of the transformation between the parent coordinates psi and the global coordinate x over here, and then it will be used to calculate the gradient of the shape function. So once we have these operators, then actually it's like the operator that already developed in MoFEM, and we just use these operators. And once we have these operators, we just push it to the left-hand side pipeline, as I mentioned in the previous slide. The next operators that will be pushed to the left-hand side pipeline is the operator that calculate and assemble the element stiffness matrix. So you can see over here, we loop over the integration points as expected in any other finite element program. And then in that loop, we have two nested loops that loop over the row and the column data to calculate the element stiffness matrix according to the formula you can see over here on the left-hand side. After each loop, the data for the base functions and the integrating weight will be shifted to the next one. You can see over here. I think it should be mentioned here that we use the F-tensor library that use the Einstein notation. And you can see here the index I is a special variable that enable the summation. So the next one for the right-hand side pipelines, similarly, we have the user data operators that's responsible for the calculation of the right-hand side vector implemented here in the same manner in the previous slides, and then that will be pushed to the right-hand side pipelines. Here, I just want to also mention that the code for the left-hand side and the right-hand side that we see in these slides are just the definition step of the pipelines and the user data operators. All of the actual calculations will not be executed here, but in the function of the source system, which we will show later. So basically, this one is just the definition and no calculation when we run the code. The next function is the one for setting integration rules. So you can see over here, we can set the integration rules that we would like to use for the left-hand side and the right-hand side separately. As we are able to set the different integration rules for different operators separately, then there is a potential to save computational effort in case the functions that need to be approximated have different polynomial orders. The next functions over here is the solve system function. So here's the place where the system of equation is solved. In this function, I would like to focus on two things. The first one is the discrete manager, and the second one is the KSP solve. So the discrete manager is the PESI entity, and PESI is the library for scientific computation developed by researcher at Argonne National Laboratory. And this discrete manager asks MoFEM to give it a matrix and vector, and then MoFEM would call the pipelines for the left-hand side and the right-hand side and execute all the user data operators that has been implemented and then provide it back to the discrete manager. For solving the system of equation, here we use the KSB solver, also provided by Paisson. And this function, KSB solver over here, is where all the loops and the calculation take place. The loop over the element and entities also happen here. So as you can see, MoFEM is tightly integrated with Paisson for solving system equations. So the last function that's responsible for the post-processing is the output results. You can see here, first we clear the pipelines that we created, that we had before, and then we generate the reference mesh. We add the field we want to be outputting, and then we replace the right-hand side pipeline for processing. Then we look over the final elements to obtain the field value, and then finally we write the output in the H5M format. So the video over here show the process of developing and running analysis in MoFEM. So the code normally divided in CPP file, where we have the main function, and the HPP file, where we have the user data operators. So once the code is developed, we compile the code, for example, in the terminal. And once we have the binary file, we can run the analysis by specifying the input file name, the order, and then we use the MB convert to convert the output format to the VTK format that we can open in Paraview. You can see over here, and then we can use the filter in Paraview in order to visualize our result. Okay, so there are several possibility for extensions over here. So the code that I just showed you is for 2D problem, 2D Poisson problem. So with minimal effort, you can extend it to 3D by just changing just few lines of codes. It is also straightforward to extend the code to cover non-homogeneous boundary condition, or you can see over here, non-linear problem, for example, non-linear minimal surface equation. You can also extend it to cover the time-dependent problem. For example, here we have the time-dependent wave equations. The tutorial from SCL 1 to SCL 7 over here, we walk you through all of the implementations of the extensions that I mentioned. Even though there will be work to do with the text of the tutorial, but the codes are available for you to play with if you are interested. That led me to the summary of my part of the presentation. So I have shown you the general structure of the program developed in MoFEM, implementation of user data operators to calculate the left-hand side matrix and the right-hand side vector, then how to push it to the pipelines, and then running the analysis and some possible extension of the code. So I hope that you will find MoFEM interesting and consider to join the MoFEM community. Thank you for your attention.
Thank you.